for a while now, but I'm just going to make a quick call out. We just started a program at OSGi of testimonials where we will be putting testimonials up on our public website. Initially, it's going to be on a testimonial page. Eventually, once we gather enough testimonials, we're going to move that to the homepage. But we're just opening up the program, so we're waiting to build up a list of testimonials. If you're using OSGi, you don't have to be a member. Just tell us your experience. Tell us your positive experience, and we'll try to get you up there. So I'm going to leave that up while I'm talking. It's my pleasure. For the past few years, we've been at the OSGi Alliance trying to acknowledge individuals and organizations that have made extraordinary contributions to both our community and our technology. And once again, I have the pleasure of making 2 awards. One is for individuals, and the second is for an organization that has shown leadership. And they are aptly named the OSGi Alliance Leadership Awards. The first award is going to somebody I've known almost 20 years. Hans-Werner Bitzer with Deutsche Telekom was one of the original members of the OSGi Board of Directors. He started shortly after the organization was formed and served for well over 10 years on the OSGi Board of Directors and was a staunch advocate of the organization and the technology. Hans-Werner was fundamental in getting Home Gateway Initiative, HGI, to adopt OSGi technology in their execution environment, which became a platform for many telecom operators to deploy OSGi technology into the residential setting. And in fact, that is the reason that EclipseCon, which is the Deutsche Telekom platform, is OSGi based, fundamentally. And it's in well over 1 million deployments at this point. I can't say enough about this guy. He has been fundamental in propagating OSGi technology and showing the benefits of it to a whole host of different folks in the telecom sector and in the residential sector. And with that, I'd like to welcome Hans-Werner Bitzer, please.
Let me say a few words. Thanks, Dan. Thanks to the board members of the OSGi Alliance. I remember very well back in 2000 when we sat on a panel at the original launch event of the first OSGi specification 2000 in San Diego at a connections conference, and we were sitting on the panel explaining to the audience and the journalists what gap OSGi technology should fill in our views. And we were giving the visions of our respective companies that we had for that. So I speaking for the telcos, and as you said, I was quite glad that after many years of building the spec, doing research projects, and building prototypes, my company came out with a commercial product based on that technology. And if I look in the US or in Asia, there are other major telcos having this technology in their residential offering. I think now the time has moved on, and residential and smart home is just one part of the big IoT world, and there's big new challenges coming with the non-consumer part, like the industrial IoT. And I think there's a lot of new challenges, but it's a lot of similar challenges where OSGi can make its mark. And I want to give one other aspect of a telco perspective. I think in this IoT area and digital transformation, one key layer is the connectivity, and we know what's coming with 5G, and the organization relevant there is 3GPP doing these specs, and this is well established. On the next layer, on the service layer, there's another organization that's equally organized, the same SDOs form a public partnership. It's called 1M2M. It's not as established, but they address the next layer where there needs to be, I think, standardization to, let's say, cope with the fragmentation we still have on that layer. I think that is a big thing for the future, that these two organizations develop their specs, and I'm glad that we kicked off an interworking work item between OSGi and 1M2M. And so thanks again for the award. It comes in the right moment. I will stop working for Deutsche Telekom, but I definitely stay in the area of IoT, where I think OSGi will keep on making its mark. Thanks, everybody.
So I can't wait to see what comes next out of this 1M2M stuff. All right, with that, move on to our organizational award. It's kind of hard to look at our organization today, the OSGi Alliance, and not notice the amazing contributions from our next award winner. The CTO of the corporation is going to accept the award, but the contributions come from many. I'm going to read the plaque because it sums it up well. Given an appreciation for extensive initiatives and activities in support of the OSGi, including board, officer, and strategic leadership, marketing committee chair, and IoT expert group co-chair leadership, technical submissions and initiation, and contribution to many other Alliance programs. They actually hold 3 officer roles at the Alliance. Treasurer and EG chair, expert group chair, and vice president of marketing. The organization is Paramis, and accepting for Paramis today is Tim Ward, their CTO. Tim? So I'm not going to let him off the hook. Stand up, Mike. Stand up, please. Turn around. Mike Francis, our Vice President of Marketing. His excuse was he had to take the pictures. So, Tim.
Well, hello everyone. As you've heard, I'm Tim. I'm CTO at Paramis, and we're a pretty small company, so it's possible a lot of you haven't heard of us. But we've been involved with the OSGi Alliance now for 11 years. I think we've had, so Richard, our CEO, has been president in the past. We still hold a number of board positions. And looking back, actually, I can kind of see why people have maybe heard of us when they do get involved with the OSGi specs, because going back probably release 4.1, the first remote services spec was probably where we got started. There have been 4 different remote services specs since then. All of them have our fingerprints on them, stuff in R7 that you're seeing now, so things that are happening in en route, things that are happening with the JAX-RS whiteboard, transaction control. All of this stuff is things that we've either been involved with because we think they're good ideas or because we've had customers who really want this stuff to happen. And what we've seen over this period is just this huge passion for OSGi technology. We think it's great, and if you haven't been using it, although I imagine most of you have, then you should just keep staying involved. It's getting better and better. So thank you, everyone. Thank you, Dan. And I'll let you continue.
Thanks, Tim. As Tim said, they're not a huge organization, but they're heart and soul in OSGi. So now it's time. I'm running almost exactly on time. Surprise, surprise. It's time to introduce our keynote for today. Topic is literally out of this world. Can't. And our 2 speakers are Anthony Walsh with the European Space Agency. And let me tell you a little bit about Anthony. Tony is a software engineer working in the European Space Agency. He has over 20 years of experience in the development and management of software within the space domain, and he is currently the technical systems manager for the adoption of EclipseCon at the European Space Operations Center. You'll get the acronym explained in a moment. Tony has a degree in astrophysics from the University of Edinburgh and a master's in space engineering and astronautics from Cranfield University. Joining Tony today is Hristo Inzovic, and he's with Telespazio Vega Deutschland. Hristo is a software engineer working for Telespazio Vega Deutschland, and he has over 12 years of professional experience in design, development, and management of complex software systems. For the past 3 years, he has actively contributed to the integration and validation efforts connected with EclipseCon. He is currently lead of integration and development team and participates in the design and implementation of system concepts as an architect. Hristo has degrees in computer science from the Technical University Darmstadt and the University of Plovdiv. I'd like to welcome our speakers for what I'm very much looking forward to is our keynote today. Tony, Hristo, come on up.
So thanks, Dan, for the introductions. So good morning to everyone. I think I quickly just need to flip over the presentation. Okay, so I guess some of you may have seen the title for the presentation, and I guess maybe you've asked what OSGi has to do with Jupiter. Good question. And what I will do is present today is what we're doing at the European Space Agency in using OSGi to develop the next generation of mission control systems, which we're first going to use on a Jupiter mission. It's going to Jupiter and exploring the moons. It's called JUICE, which will be launched in approximately 2022 and will be operated from the ESA Operations Center, which is based in Germany, in Darmstadt. So the first part of the presentation will just be a general introduction into mission control, what we do, the JUICE mission, talk a little bit about ESA and what we do at the Operations Center. The main part of the presentation will be given by Hristo, who will then really talk about how OSGi is being used in the software development. So a little crash course in spacecraft mission control. So here's the very basics. So the operators use what we call a mission control system to operate the spacecraft. So they create commands to make the spacecraft do what they want it to do. These then get encoded as telecommands, which are transmitted to the spacecraft. The spacecraft does what it's supposed to do, and telemetry comes back to give the status, and the status we are able to view through the mission control system to make sure it does what it's supposed to do. In low Earth orbit, this is fairly easy. You send a command, you ensure or get some data back, and you just check what the spacecraft is doing, what you expect. As soon as we start to do missions such as the JUICE mission, then it becomes harder. So Jupiter is a long way away, I think somewhere about 600 million kilometers. And the time to get there at the longest time is about 55 minutes. So obviously what we can't do is send a command, wait to get some data back, and check that it's okay, and then send another command. So what happens is we create a whole schedule of commands using the mission control system, uplink them to the spacecraft, then wait some time, we then retrieve all the data, and then check excuse me, what the spacecraft does, what it's supposed to do. Obviously we need to get the commands and the data to and from the spacecraft. So At ESA, what we have is a network of ground stations which is able to communicate with the spacecraft. So in total, we have about 7 stations in the core system, and we have a number of what we call deep space antennas. We have 3 of those, which are quite big antennas, 35 meters, and they're needed because, obviously, for JUICE, it's really a very long way away. So the signal, obviously, by the time it gets to the spacecraft, will be very weak. So we need to send a strong signal, and obviously, when the spacecraft sends the signal back, it's very weak when it reaches the Earth, and therefore, again, we need a very big antenna. And at the operations center, we also have an operations center for the ground stations. So the ground stations are actually operated in a very similar manner to the spacecraft. So they're all remotely controlled. Most of them don't have people based permanently at the stations. So we have a control center which is operating the ground stations and also planning the ground stations, because these tend to be things that are shared across different spacecraft. And together, these are the 2 main centers for the mission control system and for the ESA track, the ground stations control center. And the new system that we will be developing based on OSGi will be covering both of these, both for mission control systems, and if everything goes well, then we will then use the same system for the ESA track control center. So just a little bit about the actual JUICE mission. So JUICE stands for Jupiter Ice Moons Explorer, and this is going to visit the Jovian system, and the main focus is really to focus on the study of Jupiter's main 3 moons, Ganymede, Callisto, and Europa. And the spacecraft is being developed by Airbus and will launch in 2022, and it's a long way to Jupiter, so it actually will take 7 years, so it arrives 2029. So we'll use a number of gravity assists to help fling the spacecraft out to Jupiter. So actually there'll be 5 in total, first via Earth, then a flyby by Venus, Earth, Mars, and again finally by Earth, which will then sling the spacecraft out to Jupiter so it gets enough velocity to actually get out to Jupiter. Once it gets to Jupiter, we'll go into orbit and go around Jupiter and study the different moons. And then finally in 2033, we'll actually go into orbit around Ganymede, which will then be the main focus of the mission. And I think actually will be the first spacecraft ever that will be in orbit around a moon apart from our moon here going around the Earth. And it has quite a number of instruments, so cameras obviously for taking pictures of the surface, spectrometers for looking at the structure of the materials of the surface, and also materials being sent off from the surface, magnetometers to measure the magnetic fields, and also ice penetrating radar. And the main objectives are to really study Jupiter and its moons, and particularly the moons. So these moons, the 3 moons I mentioned, are actually extremely interesting. So rather than being just balls of rock that originally people thought they were, actually they're ice moons. So they have a large part of it is made of ice. And what's really interesting is actually these moons, we believe, have oceans, so liquid water under the crust, the icy crust of the moon. And that's actually very interesting, because obviously where there's water, then potentially there could be life. So one of the main focuses for the mission will be to study the moons and see if the conditions for life would be suitable. So it's not going to go and actually find life. Well, it's not intended to do that, so we won't be getting pictures of little green men, I don't think, but hopefully we'll understand more and understand whether actually life potentially could be there or could be there in the future. So, as I said, it will look at many different characteristics. So we'll look at try and understand the characteristics of the ocean layers underneath the crust, the topology, the geology, characterization of the icy crusts and the internal mass distribution, dynamics, and also finally Ganymede, which has its own magnetic field, to understand more about why it has a magnetic field and how that interacts with the Jupiter's magnetic field. So, as you can imagine, going into space isn't cheap. Returns are great, but actually space is expensive. So JUICE mission is somewhere about 850 million euros. So it's expensive. Some missions we do a bit cheaper. There are some that are even more expensive than that. And then you can imagine that actually this can be quite hard to justify for any one nation to do these types of missions. So what we tend to do is share the cost amongst nations, which makes a lot of sense, that you get the same return, but each nation is spending much less money. And to do the coordination of this, then this is the reason why the European Space Agency was created. So the idea is that it coordinates these space activities between European nations to basically take all the resources, the funding from the different member states, and use them and maximize the return for each nation. So just a little bit about European Space Agency, ESA. So it started approximately 50 years ago. We have now 22 member states. It's actually not a member state. It's not actually an EU organization. It's actually completely independent. So some of the member states actually are not EU countries. Most are, but not all EU countries are members of ESA. We have about 8 facilities through Europe. There's 2 here in Germany, one in Darmstadt, the Operations Center, and the Astronaut Training Center up in Cologne, and with about 2,300 staff. So the budget overall is, well, last year was 5.75 billion euros. So this is mainly coming from the member states. So part of it is mandatory contributions you have to pay if you're a member of ESA, and also optional programs so member states can sign up for. And also there is some funding, or quite significant funding, coming from the EU for some of the EU space activities, so in particularly Copernicus and the Galileo systems. And so far, over 80 satellites have been designed, tested, and operated in flight. And ESA is really covering all different areas of the space activities. So obviously space science, which is what we're talking about today with JUICE, human space flight. So there are astronauts on the ISS. ESA has a module, the Columbus module on the ISS. Exploration. So, for example, in 2020, there will be a robotic mission to Mars, and there will be a lander and a rover. Earth observation, space transportation. So ESA were responsible for the development of the Ariane rockets. Navigation, so maybe most of you have heard of Galileo. ESA were heavily involved in the procurement of Galileo. Development of technologies that help the European industry be more competitive, and also telecoms. And the area that I'm involved with is with operations. So operation of all the ESA spacecraft, as I said, which is done at the European Space Operations Center. So the center is, as I said, is the main center where we operate spacecraft. We've been operating nearly, well, over 50 years. It was started in 1967. And we do mission operations and also launch operations. So we actually do sometimes purely the launch. So we have, for other organizations, done the launch phases, and then we hand the spacecraft over to the organization to actually operate. As I said, we have a network of ground stations around the world, and also we are a center for other things, such as particularly space debris, space security, space system engineering. And the missions we operate are really focusing on the scientific realm. So this is Earth observation, astronomy, and solar system exploration missions. So just to give you an idea of some of these missions, so you can see here we have quite a few. We have at ESOC over 81 and counting. There was a launch of EpiColombo. Some of you may have seen it in the news. That was launched, I think, last Friday, which is a mission that's going to Mercury. And just to give you a flavor of the different types of missions, I was just going to run through just some examples. So one is Cryosat. So Cryosat is a mission that we're doing to monitor the variation and extent of polar ice. So it can really monitor the thickness of ice right down to 1.3 centimeters. And obviously this is very important now with trying to understand the impacts of climate change. So really getting a good understanding of how the ice sheets are changing. So we know that, for example, the polar ice sheet is really changing dramatically. Obviously we need to understand that and see how that correlates with the models of how people expect the ice sheet to change. So this was launched in 2010, and like many missions, although it was intended just to run for 3.5 years, it's now still going strong and probably will continue into 2020. Another mission is an astronomy type mission. So an example of this is Planck. So this is mapping the cosmic ray background. So this is really the afterglow from the Big Bang. So about 380,000 years after the Big Bang, the universe was very hot. So basically it was a hot plasma and cooled enough that actually the protons, electrons combined to form neutral atoms. And before this point, then light, basically, it was opaque to light because the light would be absorbed very readily by the ionized atoms. And after this point, basically, the universe becomes transparent. And we can actually see this kind of imprint of when this happened. And this is kind of a fundamental thing to cosmologists to actually look at this cosmic ray background and understand the variations that we see. So actually the cosmic ray background is extremely uniform, but there are some very small variations which eventually would be the things that would be the seeds for the formation of galaxies and clusters of galaxies. But to measure this, then actually what you need is a very cool instrument, because if you try to measure this in the microwave, then you have thermal noise from the instrument. So what we had to do was use liquid helium to cool the instrument down to, well, literally absolute zero, so 0.1 degrees above absolute zero. And actually at the time it was flying, it was actually the known coldest object in space. And this operated until 2020 when the helium was exhausted. Another example of the exploration missions is Rosetta. Maybe some of you probably remember this. There was quite a lot in the news a few years ago. So this was a study of comet 67P, and Rosetta was actually placed in orbit around the comet. So it stayed with the comet when it came into the solar system during its active phase and released a small lander called Philae, which successfully landed on the comet and gave back data for approximately 2 days until the battery power ran out. So this has actually been significant in helping understand comets. In particular, one of the things that was found was that the water that you see in this comet is actually very different from what we see on Earth, which is interesting because actually one of the main theories has always been that comets were seeding the Earth with the water. So all the water we see in the oceans was actually seeded from comets crashing into the Earth early on in the solar system. But actually, when you look at the water that we see in the comet and the water in the oceans, actually it's quite different. It's a different isotope type of water. So that's actually an interesting result. So maybe we have to think a little bit, or maybe this comet was not typical of comets, and maybe the theory is correct. So it's actually something interesting for the scientists to look at. And this was launched in 2004 and took 10 years to arrive, and then operated until 2016. So you can see from the Rosetta mission and also from JUICE that these missions really go on for a long time. So sometimes these missions go on for 15 years, sometimes 20 years. And if you include the development phase for the missions, and sometimes we're really talking about 25 years from the conception of a mission right through to the end of the mission. So, as I mentioned, what we're doing at the moment is creating a new generation of monitoring and control systems, and for at ESOC and for the JUICE mission. But this is actually not being done in isolation. It's actually being done as a bigger activity for what's called the European Ground Systems Common Core, or EGSEC. So actually within Europe, there are actually many different systems that are being used for monitoring and control, both for operations and also for the spacecraft assembly, integration and testing. And actually now many of these are reaching the end of their life, and it was actually agreed through the different stakeholders in Europe to actually develop a common infrastructure that can be used by all the different national agencies, by ESA, by prime industry. And therefore, based on this agreement, a project was started, an ambitious project, which is a collaboration between ESA, the agencies and all the industry to modernize their systems based on a common software infrastructure. And this is really what the topic is about today, is that OSGi is a core pillar within that infrastructure. So the project itself has now been running for quite some time, so over 5 years. So the development initially started with the requirement specification and technology evaluations. A number of criteria were taken into consideration for the selection of the technologies. An important one was that we need something which is modular and extensible for the different missions. So this was an infrastructure that was going to be used by many different missions, many different types of missions, and therefore it was very important that it's possible to remove parts of the system, replace it with other parts of the system, add additional functionality by extensions. Obviously, we have certain requirements on performance, reliability and scalability, which is important for mission control. Another consideration was licensing considerations. So this software is something that will be licensed within Europe, so we had to pick technologies which would be compatible with this. As I mentioned, we have very long missions, so another aspect was understanding the longevity of the technologies and how we see it being supported in the future, and also just generally the community strength, so the knowledge of the technologies both inside and outside of the space domain. So a number of technologies were considered. I won't really go into this because it's not really the topic of the presentation, but we looked at things like EJB, service component architecture, Corba component model, OSGi, and in the end, OSGi was selected as the most appropriate solution. And then this was input into contract for the industrial consortium, which was then responsible for the implementation, which is where Christo will take over, and he's going to now talk about actually the industrial side and how OSGi is being used in the implementation.
No, it's not. Okay, I guess. Is it on now? Yeah, it's on. Okay, perfect. So, good morning, everyone. As Tony said, I'm going to talk about the industrial side of things. Oops, wrong side. So basically, what you see here is the consortium that was selected to implement the GSSE system. For me personally, this was the first project with such a big consortium. I'm also quite new to OSGi myself. I joined the project 3 years ago, and this is actually the first time I commercially deal with the OSGi specification and its implementations. I am part of the, whoa, is this working? Yeah, do you see anything? No, not really. Okay, anyway. So I'm part of the Telespazio Vega company, and as you see, the consortium is basically split into several parts. We have the core team, which is Telespazio Vega, CGI Thermo, and GMV. Telespazio Vega is the prime of the consortium. Attached to the consortium, we have 2 sub-consortiums from Italy and Belgium, and also several companies that are not part of any sub-consortium, but basically build up the entire consortium. As Tony said, the project EGSCC is not really meant to suit only a single mission. It's not developed specifically for Jews. It is developed to suit many missions and various contexts. The interesting thing is that the project is being developed now for roughly 5 years, I think. They had an initial phase with a specification when the specification was done, and now the development has been going on for 4 years. So basically I joined 3 years ago. The development was already 1 year in progress, and getting in there with OSGi and with specific space domain, terms, and it's kind of hard for a software engineer to begin with, because I am a pure software engineer. I have not dealt with the space domain before, and this was quite challenging for me at the beginning. Let's see how the project is organized briefly. First of all, just some statistics. So the project spans 8 countries. It has 17 companies in there, has 23 teams and 43 components. What are components? I'm just going to briefly mention. Components are, for example, Tony explained what an MNC system is. You have a spacecraft, it sends data back to Earth, and then it receives data from Earth. So a component, for example, is something that receives the data. Then you have another component that decodes the data that you've received. Then you have another component which stores the data that you have received. Then you have another component, for example, which encodes the data that you want to send. And this is all basically, components are units of functionality which do a specific thing inside the MNC system, the monitoring and control system. The project at the moment has 11 system architects. System architects are responsible for defining system concepts and basically explaining to the developers how they should be realized. I originally joined the team as integration and validation engineer. Then I moved to being the leader of that team, the integration and validation team. At some point I was involved in development of components. I was a component developer, then I was a component lead. And from this year, for a few months now, I'm also involved in the actual monitoring and coordination team, the MCT team, where the architects are. How is this whole thing put together? What technology stack do we use? We have a technology baseline which is defined. It was predefined when I joined, and it changes very rarely. It's because of the nature of the space missions, where you want things to be stable. For missions, things need to be fixed. You don't want to change technology every 6 months. You want something that you know it works and it will continue working for 20 years, and you don't want to bother with upgrading it because you don't know what the consequences are going to be. So the technology baseline is fixed. We have 2 setups. One is called the SDE development environment, which you can see what it contains. It has Eclipse, Maven, Git, Groovy, OpenJDK, and so on. We are also fixed on the versions of the operating systems which we use. Currently we have OpenSUSE 13.2 and /12. We also have another specification for an SDE for the continuous integration, which is built on top of SonarQube, Nexus, Jenkins, Maven, and so on. The versions you see here, we are fixed on Java 8 right now, and Maven 3.2.3. We use Apache Service Mix 5.4.0, which includes Graph 2.4.1, and this is basically the specification version we are fixed on, so it's version 5. We use Eclipse Luna also as a baseline, and the operating systems I already mentioned. This is an actual page from the technology baseline. I just wanted to show you how it looks. So that's a huge document. It has 161 pages, And it defines exactly in detail what you are allowed to use and what you're not allowed to use, and also gives you sometimes directions on how it is supposed to be used. Now, let's talk a little bit about what eGCC actually is. So I said to begin with, it has 43 components. And the reality is that the eGCC software is a infrastructure which is designed to support distributed space monitoring and control systems. It is a layered system. It has basically 3 layers. It has the kernel, reference implementations on top of the kernel, and also test facilities. All of those layers, they are further decomposed into the components that I have mentioned previously. The components are, depending on the mission, combined in different ways, and then you get the eGCC applications, which actually can do something, because components by themselves, you know, if you have a component that just stores, it doesn't really give you a lot of things, yeah? So you want to have like a set of components that do particular task, and this thing is called the eGCC application. This is a conceptual overview of how eGCC is put together. As I said, we have components, and components are further decomposed. Oh yeah, you hear me saying composed and decomposed a lot. Are further decomposed into implementation components, which are then composed into deployable units. A deployable unit is basically another representation of the component, but meant for deployment only. So if you have a component which has a server part and a client part, then you have basically, you can split it in 2 deployable units. One deployable unit is going to be deployed on the client, and another deployable unit is going to be deployed on the server. Now, when you combine all the deployable units and basically the components, you have applications. And then you have a combination of the applications, which is called a system. And then in the system, you can actually mix up the applications in different ways to form sessions. And the sessions can then be started. And the session is actually a grouping of application that is designed, of applications that is designed to perform a particular task. Now I'm going to talk about each part of the conceptual model briefly. I don't want to get into too much detail. The first thing I want to say is the system is model-driven. the component framework. It is used as a building block. On top of this framework, all the EJC components are implemented. It provides the entry point for components. It also controls the life cycle of components. Because in EJCC, the life cycle of a component, or an implementation component in this case, is not necessarily the same as the OSGi life cycle of a bundle. To basically compose the deployable units, you combine implementation components together. And those implementation components, as I have shown in the diagram, they also have ports. So sometimes you would want those ports to have a specific wiring. Sometimes you would not want this. The default scenario is that you let the component wire itself, but sometimes you might want to have this wiring. So by default, you have a default wiring for internal components. When I say wiring, this translates directly to blueprint. Yes, blueprint. Let me show you how a deployable unit is defined in the model. So this is how a deployable unit looks like. You have basically the same thing as a component, the implementation components that you have defined previously in the decomposition, you use to compose deployable units. From this model, from this picture here, or from what is in the model, you get deployable unit, which is again generated. It is basically a Maven project with packaging deployable unit. And what it has is the list of all the dependencies, which are already known to the model because they were defined in the model previously. And also it has wiring representation of what or how you want to wire the different components inside. This wiring is not blueprint. This is something platform independent. It is internal to the project. So till this point, it actually, you have no connection to OSGi whatsoever. It's absolutely abstract. It's all in the model. Once you start generating it, it then gets tied to OSGi. And this is just basic comparison that I have done for myself previously when I started working on a project, because when you start working somewhere and you know, okay, OSGi is used, the first thing you do is kind of read the specification, right? So this is what I did. And when I read the specification, in my head, the picture on the left side popped. Yeah, so you have an OSGi bundle, it's a nice boundary, then you have whatever your classes and your beans, they are put together with Blueprint, and then Blueprint consumes and provides services for you. This is not how it's done in EJCC. As I said before, we have this thing called the component framework. It sits on top of OSGi. It still uses Blueprint to wire implementation components, but it's not what you would actually read in the specification. It's done differently. Every implementation component has its own entry point, which is not an OSGi entry point. It's an EJCC entry point. This entry point is basically the outside interface towards an implementation component, and then all the set of entry points is collected and then Blueprint wires them. Okay, so after the definition of deployable units, you want to build applications, and applications again is a composite and it's composed of deployable units. Basically, for every deployable unit in your application, you will get a wiring, and for the entire application, you'll get a feature, again, listing all the dependencies you have. And this is something you can actually deploy. You can put this in an OSGi implement container, and you can actually run it. Just for your understanding, I'm going to explain how the wiring is converted to Blueprint. So on the left side, you see like a summary of the format that we have that comes out of the model. So we have a boundary port section, and you have composition, the internal composition of a component. For every implementation component which is defined in deployable wiring, in Blueprint you get a section, which is called the component section, with references which correspond to the consumer ports, and services which correspond to the provided services, and a bean which actually instantiates the component itself. This is how the application generation works. You have a list of deployable units on one side, you combine this into an application, and then an application is generated in the form of a list of deployable units, a wiring for each deployable unit, then all the wirings are combined into a feature, which then goes together with the features of the deployable units in an application feature, and this thing you can run. Again, from the applications, you go one level up, and you compose a system. And as I said, a system by itself doesn't really work. It needs to have sessions by design, and the sessions are what groups the applications inside of the system in functional sessions. And then this is actually what you start from a EGACC user. You start a session. You do not start a deployable unit. You do not start an application. You start a session. And the session is defined inside the system. So what you have is a deployment plan, which defines what sessions do I have in my system, what applications do I have in my system, and how the applications relate to sessions, and also how applications relate to nodes. And by nodes, I mean the runtime where you actually run it. It can be a physical, virtual node, it doesn't really matter. So the interesting part here is that the EGACC deployment is actually static. You cannot change it at runtime. It is static because the deployment plan contains a static mapping configured at deployment time between application, sessions, and nodes. This is how a typical deployment looks like. You have nodes, of course, I mentioned. Inside the nodes, you have OSGi frameworks. And in every OSGi framework, you have the EGACC leader application. The leader application is a special type of application. It does not really serve any specific space-related function. It basically supports, on top of OSGi, the functions that EGACC system requires. So, for example, you have the component framework in there, which basically gives you the ability to put components together. You have application control in there, which gives you the ability to control nodes, start applications, stop applications, and so on. And you have the EGACC distributed services in there, which makes the connection between nodes and allows applications to use remote services as if they were local. All of this is built, the infrastructure is built on top of Zookeeper, and the latest implementation of the distributed services is put on top of ActiveMQ. Every node has this leader application, and there is one special node here. This is the master node. It has a leader application, which is again a little bit special. It's called the master application. It has one additional component called the EGACC runtime management. This component makes the connection between applications and sessions for a user. So when a user wants to start a session, the runtime management knows from the deployment plan which application needs to go where and which session contains which applications. Runtime management is basically the front to the for the users of EGACC. With runtime management, you control application control, which then lets you start nodes, start applications, stop applications, remove applications, whatever you need to do. Application control gives you possibility to do it. So all of those three components that I just mentioned, they are called the EGACC component framework. Called the EGACC infrastructure. So the component framework, application control, and distributed services, they are internally called the EGACC infrastructure, and this sits on top of OSGi. As I mentioned previously, it basically provides you with some facilities so that you can build your components on top. it is not 100% implemented according to a specification. This was a design decision made for particular reasons. However, what it provides for you is the so-called EGCC activator. Now, that's not the OSGi activator. That's a special thing called the EGCC activator. And every component implements an EGCC activator. And every component, if it wants to basically be hooked into the EGCC lifecycle of components, it needs to implement specific hooks for this reason. This is how a base class looks like. This is generated from the model. You are not allowed to touch this. You basically get it and you have to implement it. When you get this class, you basically subclass it and you implement the 2 or 3 methods in this case: init, start processing, and stop processing. The component lifecycle, I said previously, is not the same as the OSGi lifecycle of bundles. Init is basically more or less equal to when init finishes, you know that your bundle is active. So it has status activated. So after that, there is an additional phase which calls the start processing on all of the bundles. And you want to make sure that when you call start processing, all of your consumed services and provided services are being either consumed or injected into your component, or provided services were actually put into the service registry. I talk a lot about services and EGCC services, but what is actually an EGCC service? An EGCC service is, again, something really specific to EGCC. A service is something which you can mark with annotation at service, which tells the developer this is a stateless service, this thing does not contain any state, or you can mark it with a conversational factory interface, and you know that this is a stateful service, and you can actually inject callbacks into that service so that it notifies you for a particular event. This is again put on top of OSGi. The component framework listens for services with those annotations and performs specific modifications to the services, like it adds specific properties. So in any given point in time, you actually have 2 registrations of a service and a container. The first is the original registration, and then the second one is the service that the component framework re-registered for you, and you basically don't see the first one. It's completely hidden from the user. Those are some of the properties we use. Some of them you might recognize, some of them are specific to EGCC. Now, this is how you put components together. Now, let me talk a little bit about application control and what it actually does. As I said previously, it is responsible for starting nodes, starting applications, stopping application, basically dealing with all the deployment-related functionality. It can monitor the nodes, it can monitor the applications, you can get specific data back from the nodes concerning the health and so on. And it is implemented on top of Zookeeper. So basically everything that application control does internally goes through Zookeeper. So, and again, let me clarify this a bit more. You have a master node with a master Karaf container. So in EGCC, a node is basically a Karaf distribution. This is the thing that basically summarizes a node. A Karaf distribution, in the Karaf distribution you have a root and you have children. And the root is always the leader application or the master application. The services that it provides those are the main services, 3 of them. It has system control service, system status service, and monitoring service. System control service just controls the nodes and application. The status service can give you particular information about the state of the system, and the monitoring service you can use to subscribe for health events if you want to monitor the system. So The first time when I read specification 7, which is out for a few months now, I thought, is what we have actually an implementation of the cluster information specification? Or can it be an implementation of the cluster information specification? And the answer is no, it's not an implementation, but it quite easily can be an implementation. Currently, we do not implement the node status service, but the system status service can give you the collection of all nodes and can give you health information, and it basically can be adapted to implement the cluster information specification. Now, going to the next part, the distributed services. Distributed services contain two parts, a service registry and an implementation of procedure call. This thing sits again on top of Zookeeper and ActiveMQ I mentioned previously. Zookeeper is used as the service registry, and currently ActiveMQ is used as the actual transport layer for remote procedure calls. I say currently because distributed services has gone through a couple of stages. The first implementation of distributed services was completely peer-to-peer. The registry was peer-to-peer and the communication was peer-to-peer. And this was working, we had it in place. The problem was that later there was a requirement on the system that changed, or maybe it was overlooked to begin with, and because of security constraints, we had to change the technology we used back then. This was a decision taken maybe 2.5 years ago. Currently, the implementation sits on top of ActiveMQ. So the service registry is basically the thing that takes my services and as an application, publishes them in the registry, and then consumes other services from other applications which are also published in the registry. The implementation of the RCP, as I mentioned, is built on top of ActiveMQ. Currently, it is completely transparent to components. And the interesting part about it is that it supports passing arguments as references. So basically, you can pass whatever object you want to the other side as long as it's not final, or basically if it has an interface, it can go to the other side and it can work on the other side as if it actually were created in the remote container, and then when you dispose of the object, it will also be disposed of in the original container. This is a requirement for EGSCC that we support this because of the callbacks of methods that we have. The RCP also, as I said, monitors the lifecycle of instances and ensures that they're garbage collected properly. This is a brief diagram of, like, it's the more or less the whole function of the RCP is put in this diagram, and you have like the client side with a proxy which then pushes a call through ActiveMQ, and then on the other side the service takes the call and processes it. Now, the OSGi remote services specification exists for quite some time now, and currently, to begin with, I remember I was told by some of my colleagues that were longer on the project that you have, that there was research done at the time of the creation of the EGSCC distributed services, and there was no suitable technology that can actually support what we need. But right now, it is not an implementation of remote services, but again, it can be. So we have a direct concept or a counterpart for distribution provider. The endpoint, we use the services, but then we don't have a direct counterpart for the topology manager, remote service admin, and discovery, but this can easily be covered by the remote service registry. The EGSCC infrastructure by itself, although it's called EGSCC, it's actually two components or several components put together, which then are not, the EGSCC specific functionality is put on top of those components. So in theory, if you want to implement particular OSGi specification on top of them, this is possible, and it's actually not a lot of work, but if this is something that ESO would like to do in the future, we don't know yet. And for the last slide, I have prepared this. I thought I would open with a joke. So I've heard a couple of times in the industry that our prime job is not to fly a spacecraft. But we are not software developers. We fly spacecraft. So this is generally the state of mind in the industry. So let me explain a little bit about the problems and the challenges we had. So first of all, for me, this was a big project, and this big project has the so-called consortium syndrome. So basically, the consortium is formed on basically on the basis of which countries have to participate, and then the countries select which companies are going to participate. So basically, you do not choose the companies you work for, you do not choose the teams you work with, and it kind of creates a little bit of mess. To begin with, also, we had a lack of OSGi experience. So we were learning OSGi as we go, and this is, in a huge project, really difficult to backtrack, because as soon as you make a decision, you implement it, you put it in place, a lot of people adopt it, and then you discover this was a huge mistake. It costs a lot of money to actually revert it and do it again, because people already adopted it. It's not really feasible some of the times. And for example, with the practices for best practices for service dependency management, we made a mistake, but right now we cannot really roll it back. One particular thing that I want to mention is the decomposition. There were people just going crazy with the decomposition. They didn't know when to stop. Like, they were decomposing the components to the level of a service. One particular component had just an implementation component to convert from long to int. So this is just ridiculous. So when you do the composition, just stop yourself at some point. Also, one huge problem that we had is that technical discussions were regularly steered by stakeholders, and they are not really technical people, some of them, and this can really hurt your design. If you want to please a stakeholder and you take the technical decision that they propose, sometimes this is a mistake. So please be aware of this. Thank you very much. This was all from my side. I don't know if we have time for questions, but okay. Thank you very much.